Hello and welcome. This is going to be our lecture video for the Unit 7 test review. Up at the top here, I'll allow you to look up these definitions on your own. I still do have that document where I'm keeping track of all the definitions. All 10 of these words are in there, plus a few more, so you could use that. But when you come up with an example, that's up to you to come up with your own examples. All right, so let's move on to number 1. For the reaction, as we see here, we need to list the reactants, list the products, and balance the equation. So the reactants is anything before the reaction arrow. So it's the H2O2, hydrogen peroxide. The products are everything on the other side, H2O and O2. And now to balance it, we just need to go through each element and make sure we have the same number on both sides. We've got 2 hydrogens over here, 2 hydrogens over here. That's good. But then with oxygens, I've got 2 oxygens on the left, but 1, 2, 3 on the right, because this is 1 oxygen, this is 2 oxygens. So how do I balance that? Well, I can change the amount of oxygens right here without changing anything else. So I need to change it in a way that I have 2 oxygens on both sides. So I could do that by doing a 0.5 here temporarily. And this is a 1 and a 1, and it is all balanced right now. It's going to be 2 hydrogens, 3 oxygens, or 2 hydrogens, 2 oxygens on both sides. But I don't want to end with a 0.5, so I'll double everything to be a 2, 2, and 1 mole ratio. All right, number 2, write the balanced chemical equation for the word equation below. Carbon tetrafluoride. So carbon tetrafluoride is a covalent compound. It's going to be carbon is C, fluoride is F, and tetra is that prefix meaning 4. So CF4 is going to go to carbon by itself. So carbon can just be by itself. But fluorine is in Hofbrinkel, so it has to be F2. And now to balance this, I also need a 2 in front of the F2 for a total of 4 fluorines. All right, number 3, explain why chemical reactions must be balanced to satisfy which law? It's the conservation of mass. All right, if they're not balanced, then we might have more mass on one side than the other, and that's not allowed. Mass can be neither created nor destroyed, it just changes forms. So conservation of mass. All right, the general formula. So with general formulas, we're just going to use A's and B's and that kind of stuff. So for a synthesis, it's just A plus B becomes A bonded to B. So to show that they're bonded, we just write them right next to each other. This could be any 2 elements, could be synthesizing to make a new molecule. Decomposition, we have to start with something that's already bonded and split it apart. So AB goes to A plus B. Single replacement, we have something already bonded, AB, and then we have some third thing, C, and then the C infiltrates, and this becomes AC plus B. Double replacement, we have 2 things that are already bonded, AB and CD, and then they swap partners, so this becomes AD plus BC. And then combustion, it's going to always be some sort of hydrocarbon. So we'll say CXHY to show that this could be any number of carbons and hydrogens, always reacting with oxygen, and the products are always CO2 and water. And then also, this is a very exothermic reaction, creates a lot of heat. All right, with number 5, we need to figure out what type of reaction would occur given these reactants and then balance it all. So 2 things by themselves, these are always going to make a synthesis reaction because there's no bond there to do a replacement on. You might say the oxygen is bonded to itself, but we want bonds between 2 different types of elements for it to count as a replacement. All right, so what are these going to make? This is going to make CaO. That's balanced because calcium has 2 to give, oxygen has 2 to gain. And now, just to balance this, we need a 2 here, a 1 here, and a 2 here. All right, next up, we have just something by itself, so it's always going to be a decomposition reaction. because there's no second thing to do a replacement with. If you only ever have one product, it'll always be a decomposition. So what is this going to split into? It'll split into lithium plus nitrogen. Nitrogen is in Hofbrinkel, so it needs to be an N2. And now to balance this, we'll need a 2 here, a 6 here, and a 1 here. There we've got 6 lithium and 2 nitrogen on both sides. All right, next up, this is our perfect setup for a combustion reaction. We're combining a hydrocarbon and oxygen, so we're always going to make CO2 plus water. All right. Let's balance hydrogen first. We got a 3 and a 2, so we need to go with a 2-3 ratio here. And now let's balance oxygen. There's 5 oxygen on the right, so we need a 2.5 here. All right, and everything's balanced, but I don't like having a 0.5, so I'm going to double everything and make this a 4, make this a 5, make this a 2, and make this a 6. All right, next one. We've got aluminum, bromide, and calcium. So we do have a bond here, so we've got the potential for a replacement, and this ends up being a single replacement. It's not a double because the calcium doesn't have to break a bond to infiltrate this bond. It just can do it straight up and just do a single replacement. All right, so what's going to happen? The calcium will kick out the aluminum because they're both positively charged, and it will need to be a Br2 to be able to accept the 2 electrons from calcium. And now aluminum will be by itself. Let's see, to balance this, I need a 2 here and a 3 here. So I have 6 bromine, 2 here for the aluminum, 3 here for the calcium. All right, next up, we have got a double replacement. So we've got 2 bonded things that are going to swap partners. If you have 2 bonded constituents, it's almost always going to be a double replacement. So the silver is going to take sulfur as its new partner, and the sodium will partner up with fluorine. Silver's got 1 to give, as shown by the fact that it's bonded to a single fluorine over here. So I need 2 silver to bond to my 1 sulfur. And let's see. Do I need to balance anything else? I need to put a 2 here and a 2 here, and then a 1 and a 1. So that's Ag2S. All right. Balance the following chemical reactions. Let's see, 3, 2, so I have 6 hydrogens each, and then a 2 here, so I have 2 phosphorus each. Let's see, a 3 here to balance with my copper, a 3 here to balance my magnesium, sulfur's balanced, so 1, 3, 1, 3. Just make sure I did that right, just looking through every element. It's always good to double check. Balance the following equations and determine the type of reaction. So more of the same. We've got a combustion because you've got a hydrocarbon reacting with oxygen to make CO2 and water. To balance the carbon, I should put a 4 here. To balance the hydrogen, I should put a 5 here. Now I'm up to 9 oxygen. Wait, not 9. I'm up to 13 oxygen on the right. So what times 2 is 13? 6.5 times 2 is 13. And then go ahead and double everything. So 2, 13, 8, 10. Next one, predict the products. I've got just 2 elemental things, so it's going to be a synthesis. The sodium and the nitrogen will come together. Now I'll need 3 sodium to have enough electrons to fill all the spots on the nitrogen. And let's see, to balance this, I'll probably need a 2 here to balance out my nitrogens. Now I'm up to 6 sodium, so a 6 here to balance out my sodiums. Again, that's a synthesis. And here I've got a decomposition. And the zinc and the oxygen separate. Oxygen is a diatomic, so it always has to get the O2, which means a 2 here and a 2 here. All right, number 10 asks us to use the balance equation to solve the following. When iron rusts in air, iron 3 oxide is produced. How many grams of iron 3 oxide are produced if 132 grams of iron rusts? Well, here it helps us break this into individual steps. Convert grams of iron to moles of iron. So I've got 132.4 grams of iron. I just need to multiply that by the molar mass of iron. I grab my periodic table, and I see that iron weighs 55.845 grams to every 1 mole of iron. Now I grab a calculator, and I divide the 132 by 55.845, and I get 2.37 moles of iron. All right, moles of iron to moles of iron 3 oxide. So use the number from above, 2.37 moles of iron. And now I've got to look at the reaction. For every 4 moles of iron, I produce 2 moles of iron 3 oxide. So let's put that in. 4 moles of iron produce 2 moles of iron 3 oxide. All right, now I evaluate this by just multiplying by 2, dividing by 4, and I get 1.19 moles of Fe2O3, and then convert moles of that to grams of that. So 1.19 moles of Fe2O3 is how many grams I need to multiply by its molar mass. So 1 mole of Fe2O3 weighs, I've got to add it up, 2 times iron plus 3 times oxygen gives me 159.687 grams. And with that number still in my calculator, I'll just multiply by 1.19 and get 190 grams approximately of Fe2O3. All right, on to number 11. In the previous reaction, identify the following. The theoretical yield of iron 3 oxide. That is the number we just calculated, 190 grams. The limiting reactant is the iron itself, and the excess reactant is what we were reacting with, which was the oxygen, because it's reacting in air, so there's really unlimited oxygen in the air to enter the reaction. All right. In an experiment, a student produces 56.4 grams of sodium chloride. The student calculated that he/she would produce 59.1 grams. What is the actual yield? Is the pencil 56.4 grams. Theoretical yield was the 59.1 grams. Percent yield, we divide those two numbers with the theoretical on the bottom and multiply by 100%. 56.4 divided by 59.1 gives us 95.4% yield. All right. Solid aluminum reacts with hydrochloric acid to produce hydrogen gas and aqueous aluminum chloride. The balance equation is thus: a student added hydrochloric acid until bubbles stopped and then added an additional 2 milliliters to make sure no more gas would form. The limiting reactant would therefore be the aluminum because it was not added in excess. And the excess reactant is the hydrochloric acid. A student reacted aqueous iron chloride with solid magnesium, produced solid iron and aqueous magnesium chloride. The solid iron was recovered and dried in a beaker. The balanced chemical equation for the reaction is thus: the following data was collected. What is the actual yield of iron? So that would be this number right here, but minus the mass of the beaker. So 72.25 minus 70.5 72.25 minus 70.5 gives us 1.75 grams. The theoretical yield was 1.9 grams. Calculate the percentage yield, 1.75 divided by 1.93 times 100% divided by 1.93, and I got 90.7%. All right. All right, last page. What are some errors that cause a percent yield to be less than 100%? So that would be a loss of product, like if some of it gets stuck in the beaker or evaporates. What are some errors that cause the percent yield to be higher than 100%? So the only way you can get a percent yield higher than 100% is if you accidentally have some contaminants. All right, you will never get higher than 100% of actual product, but if you have some contaminants, they will increase the mass and make it look like you got over 100%. How do you achieve 100% yield? Well, just by good lab techniques. And a big way is always adding one reactant in excess will help drive the reaction to its conclusion, where whatever the limiting reaction is 100% reacted. All right, pentane is a good fuel that produces energy through combustion in the following balanced equation. If a car uses 3,500 grams of there's no way 3,500 grams is 25 gallons, but okay. Of this fuel, maybe it is, maybe it's a very light fuel. How many grams of CO2 are produced? So we'll start by writing out 3,500 grams of C5H12. And now I need to convert to moles of C5H12. So I need to know the molar mass of C5H12. So 5 carbons plus 12 hydrogens it gives me 72.151 grams of C5H12 to 1 mole of C5H12. And then do the 3,500 divided by that number to get 48.5 moles of C5H12, and then convert moles. So we'll start with the 48.5 moles of C5H12, and now we need to use our molar ratio. So for every 1 mole of C5H12, we produce 5 moles of CO2. I get those two numbers right from the equation. It's 1 to 5 ratio. So I'm going to take that number and just multiply it by 5, and I get 242.5 moles of CO2. And let's convert moles of CO2 to grams of CO2. So 242.5 moles CO2, and now I just need to multiply by the molar mass. 1 mole of CO2 weighs how much? Let's just do 1 carbon plus 2 oxygens, 44 grams, just about. And so that 44 times the 242.5 gives us 10,672.18 grams of CO2. So 10 kilograms, which is about 22 pounds of CO2. All right, that's that for this lecture video. Good luck studying, and have a good rest of your day.